Your tank level reads 0, or it is pinned at 100% and will not move. Either way, the process is blind, and now you have to find out why. Is it the sensor, the loop wiring, or the scaling in the program? Guessing wastes a whole shift. So in this video, I will show you how to test a PLC analog input properly. A repeatable method for any 4 to 20 milliamp signal. We will inject a known current and read the raw count in the program. Then check the scaling and walk a fault tree that points straight at the problem. Start at the wire, not the screen. Quick note before we dig in. This is from PLC Simulator, where you can practice analog scaling and PLC fundamentals free right in your browser. No install, no hardware. The link is in the description. Click the link in the description to try it free. Now back to the loop. First, a fast recap of what the signal even means. A 4 to 20 milliamp loop maps the whole measurement onto a current. 4 milliamps is 0%. 20 milliamps is 100%. Everything in between is linear, and that bottom end matters. The range starts at 4, not 0. That is the live 0. So a healthy loop never sits at 0 current. If you measure 0 milliamps, the loop is dead, not reading a true 0. That one fact saves you hours. I cover the full scaling math in the analog input video. It is linked below. For testing, just hold on to this. 4 is empty, 20 is full, and 0 means broken. Now the core of the test. Inject a known current and watch what the program sees. The cleanest tool is a loop calibrator. Set it to source exactly 12 milliamps, which should be 50%. No calibrator. Many transmitters have a built-in test or simulate mode that drives a fixed output. Wire your source into the input channel, then open the program and watch the raw count for that channel. On a Siemens module, the raw range is usually 0 to 27648. On Allen Bradley, it is often 0 to 32767. So at 12 milliamps, the raw count should land near the middle of whatever your module uses. If the raw count tracks your injected current, the input card and the wiring are good. The fault is downstream. Next, verify the scaling. The raw count is just a number. The program has to convert it into engineering units. 4 milliamps should scale to your low value, often 0. 20 milliamps should scale to your span, the full range. So inject 4 milliamps and confirm the engineering value reads 0. Inject 20 and confirm it reads full scale. Inject 12 and you should see the midpoint. If the raw count is correct, but the engineering value is wrong, you have found it. The scaling is off. Wrong span, wrong offset, or the raw min and max do not match the module. Practice this exact conversion free in the simulator, link below. Now the fault tree. Read the symptom, find the cause. Symptom 1, 0 milliamps. The value reads dead low or false. That is an open loop, a dead transmitter, a broken wire, or a blown fuse on the loop power. Symptom 2. The reading is pinned at full scale. That is over range, a short across the loop, or a transmitter forced above 20 milliamps. Symptom 3. The current is correct, but the number is wrong. That is scaling. Every time, go back to beat 5. Symptom 4. The value jitters or jumps around. That is noise or a grounding problem. Check the shield and the common ground. And one safety rule for measuring milliamps. Your meter goes in series with the loop, never across it. Across it reads voltage or blows the fuse. 4 smart transmitters carrying digital data on that same loop. See the heart video, link below. So here is the method, start to finish. Inject a known current. Read the raw count to clear the input card. Check the scaling to clear the program. Then let the fault tree point you at the loop, the range, the scaling, or the grounding. No more guessing which one it is. Now go make it concrete. Want to practice testing and scaling a 4 to 20 milliamp input hands-on? Click the link in the description to start free at plcsimulationsoftware.com. No hardware, no install. Subscribe, new video every Tuesday. See you in the next one.